Hello, so today we are talking about conditional probability and independence. So we've talked about the word independence before in regards to things being independent mean they do not impact each other, or one result does not indicate or dictate what's going to happen during the second result. Today we're going to focus specifically on conditional probability, which is section 5.3 of your textbook. So we're going to be focusing today on conditional probability, like we said, and this is the main definition that we're going to focus on. Conditional probability is the probability that an event occurs given we know another event has occurred. So this line right here in my formula, this stands for given. So I read this, the probability of event B happening given event A has happened. So the probability of B given A is the probability of them both happening divided by the probability of the given. So there's a little side note that the probability of A can't be 0. That's just because I can't have 0 in my denominator. So the probability has to be bigger than 0. So that's all this means. But this is the key formula that we're going to focus on. The probability of B given A is their overlap, or A and B, divided by the probability of A. So let's see what that looks like. In this example down here, it says a science teacher gave her class 2 tests. 55% passed both tests, 72% passed the first test. What is the probability, or what percent of those who passed the first test also passed the second test? Well, I'm given two kind of numbers in my problem. The first number I'm given is 55%, and it says 55% passed both. Well, if I think about where that is in my formula, the probability of A and B is the probability of the first and the second, or both tests. So the probability of A and B, we're going to say is 0.55. We're going to stick to proportions in this, not percents. So the first number I'm given, 55%, is for both, or this A and B piece. And then it says 72% of the class passed the first test. Well, if I say the probability of A is passing the first, then that equals 0.72. Well, the question that I'm trying to answer in the end says what percent who passed the first test also passed the second. Well, if I think about that in terms of this given mentality, the probability I pass the second given I pass the first, because it says what percent of those who passed the first, which means I'm given that they passed the first test, also passed the second test. So if I do the probability of passing the second given I pass the first, that's 0.55 divided by 0.72. And when I do that, I get 0.7638 or 0.764 or 76.4% passed the second given they passed the first. Move this up a little bit, passed the first. So that's conditional probability in one form. So conditional probability, my key point, tells us the likelihood of an event happening given another event has happened. And that given piece is going to be key, whether that given is in the problem or there's another word or another phrase that indicates we know another event has happened. So we're going to look at another example. And this example we're going to use for the rest of the video. It says, Shannon hits the snooze bar on her alarm clock on 60% of school days. If she doesn't hit the snooze bar, there's a 90% or 0.9 probability that she makes it to class on time. However, if she hits the snooze bar, there's only a 0.7 probability or 70% chance that she makes it to class on time. Part A says use a tree diagram to represent this situation. So we're going to focus on part A real quick, and this brings us to our second key point. The second key point is tree diagrams allow us to illustrate probabilities of multiple events. We write the probability of the outcome on the stem of the tree. So we're going to make one of these together, and you're going to see how useful they are. So if I go back to my problem, so it says Shannon hits the snooze bar 60% of school days. So if I draw my tree diagram, I always kind of start with either a person, or maybe sometimes people start with a little bar, but we have Shannon. So there's my creepy little stick figure of Shannon. So it says she hits the snooze bar 60% of school days. So my first kind of branch is snooze bar. I'm going to use S to represent snooze, and there's a 60% chance, or 0.6 chance, she hits the snooze bar. Well, that means the complement of hitting the snooze bar would be 0.4. So she either hits the snooze bar 60% of the time or doesn't hit the snooze bar 40% of the time. And these have to add to 1 or add to 100%. So this is the first stem of my tree diagram. The second thing that happens is she either makes it to school on time or she doesn't. So if I think about her hitting the snooze bar, the probability she makes it to school on time is 0.7, because if she hits the snooze, 70% chance of making it on time. So that means 30% of the time she does not make it on time, or T complement. So 70% of the time she makes it on time, 30% or the other times she doesn't make it on time, or the complement of making it on time. Well, now if I want to know kind of what's the probability of these two events happening, she hits the snooze and she makes it on time, I multiply my branches together. So the probability of snoozing and making it on time is 0.6 times 0.7, or 0.42. The probability that she snoozes and doesn't make it on time, or the complement of making it on time, is 0.6 times 0.3. So snooze and not on time would be 0.18, or 0.6 times 0.3. So this is how we use diagrams to illustrate multiple events happening. Snoozing and making it on time is 0.42, multiply my branches. Snoozing and not making it on time is 0.18, multiply the branches. Well, I can do the same thing for if she doesn't hit the snooze. So it says in the problem there's a 90% chance, or 0.9 chance, that she makes it on time if she doesn't hit the snooze. So I'll do 0.90. So that means there's a 10% chance that she doesn't make it on time, given she doesn't hit the snooze. So now if I finish out my diagram, the probability she does not snooze and she makes it on time is 0.4 times 0.9, which is 0.36. And then the probability that she doesn't hit the snooze and she doesn't make it on time, so even though she didn't hit the snooze, she still doesn't make it, that's only 0.04. So this is how we use tree diagrams, and once I have this diagram, I can answer a lot of questions because this is a lot of valuable information. So let's look at questions. So for part B, I kind of gave us our little diagram up above. So we know that there's a 60% chance she hits the snooze. And if she hits the snooze, we said that there's a 70% chance she makes it on time, or 0.42. And then a 30% chance she doesn't make it on time, or 0.18. As opposed to a 90% chance of making it on time if she doesn't hit the snooze, and then a 10% chance, or 0.04, that she doesn't make it on time. So I filled in my little probabilities. That's from part A. So B says, on a randomly chosen day, what is the probability that Shannon is late for class? Well, if I think about my tree diagram, there's two kind of branches where she's late for class or she doesn't make it on time. The first one is right here, and the second one is right here. So if I want to know what's the probability that Shannon's late for class, or what's the probability that she doesn't make it on time, I would add together these two branches. So 0.18 plus 0.04. And that tells me that there's a 22% chance, or 0.22 chance, that she's late for class. And how I did that was adding together my final branches of not making it to class on time. So part C says, suppose that Shannon is late for school. What is the probability that she hit the snooze bar in the morning? So this is a conditional statement. How I know it's conditional is because it says, suppose that Shannon is late for school. It gives me, or tells me, that she's already in one of these categories, the not on time category. So given that she's late for school, or suppose that she's late for school, what is the probability she hit the snooze bar in the morning? So I'm going to write out my conditional formula. The probability of B given A is the probability of A and B divided by the probability of A, or of the given. So what is the probability she hit the snooze bar in the morning? Meaning, what's the probability that I'm up here hitting the snooze and not on time, given that she's in one of these two categories? So A and B would be hitting the snooze bar and being late, which would be hitting the snooze and being late. That overlap is 0.18. So my numerator is 0.18, or the overlap of snooze bar and being late, divided by the probability that she's late, or the given, which we got from part B to be 0.22. So I look for the overlap divided by the given, and that gives me 0.818, or about 82%. So that reduces my kind of likelihood of hitting the snooze. If I know that I'm late for school, or if Shannon knows she's late for school, there's a much greater probability that she hit the snooze bar than she didn't hit the snooze bar. So the whole purpose of conditional probabilities is to make my denominator smaller. Instead of this being 18% chance, it's now 18% divided by 22%, which increases the likelihood of her hitting the snooze than not hitting the snooze. So key point 3, we use context clues like suppose or given or we know that to determine if the problem is stating that it is conditional or not conditional. So that's a wrap. We use conditional probabilities to model events that are under the condition that something else happened. And remember, this under the condition could say something like suppose or given or we know that. It could look a variety of ways. So we're going to have to use context clues and kind of deep analysis of the problems. Once again, section 5.3 in your textbook, go there for extra examples and to see more conditional statements worked out. So that's a wrap.